R.4 is on simplifying radicals. So we're going to use radicals a lot throughout geometry, and most of the time we're going to have what I call exact answers. So answers that have square roots or fractions and so on. We're not going to take things like 0.3 repeating. Do you guys know what 0.3 repeating is? What fraction is it? 1/3. We're not going to write 0.3 repeating as 0.3. Okay, unless I specifically ask for you to round to the nearest tenth or something like that. Okay, so we're going to try to use exact answers as much as possible. So with that, we're going to need to know how to simplify square roots. So we're going to leave things as like the square root of 2. But what if I had the square root of 9? Would I leave it like square root of 9? No, I'd write it as 3. Okay, so square roots can all go down to their simplest form. So in order to do this, we use sometimes use a factor tree. So when I first teach radicals, I usually teach it with a factor tree. So it says, try taking the square root of 72 by using a factor tree. I should have given you some room here. So if I have 72, do you guys remember how to do a factor tree from elementary school? It breaks into what factors? Maybe 8 and 9, yeah. And then 8 breaks into 4 and 2. 9 breaks into 3 and 3. And then 4 breaks into 2 and 2. So we end up getting the factors of 2 times 2 times 2 times 3 times 3. Right, do you guys remember how you used to write it as 2 cubed times 3 squared? It's prime factorization. Do you guys remember that? Okay, so here's the deal. When we're doing this factor tree, what we're looking for is what we call perfect squares. Okay, perfect squares are numbers like 1, 4, 9, 16. What's the next one? 1 squared, 2 squared, 3 squared, 4 squared, 25, 36, 49. We're looking for numbers like that we can evenly take the square root of. So if I take the square root of 49, it is going to be 7, right? Square root of 25 is 5. Okay, so we want to look for perfect squares. So let's look at this factor tree. We're going to look for pairs of items. So I have a pair of 2's, and I have a pair of 3's. What is 2 times 2? 4. What's the square root of 4? 2. So if I had this part under a square root, I would just get 2, right? If I had the 3 times 3 under a square root, I get 3. And then this one's all by itself. It's still under a square root. Does that make sense? So what we end up doing is we end up getting, for every pair that we have, we get one of them on the outside. And then every one that's all by its lonesome, it's all by itself, it stays inside the square root. So we get 2 times 2 times square root of 2, which is 6 root 2. So 72, when you take the square root of it, it simplifies down to 6 root 2. Does that make sense? So how about square root of 64? Do we know the square root of 64? It should be 8, right? Well, what happens here? It goes down to 8 and 8, 2, 2, and 2, 2, 2, and 2. So you could do it the long way if you needed to. There's a pair of 2's, a pair of 2's, a pair of 2's. So our answer is 2 times 2 times 2, which is 8. That's why it worked out evenly. There were no numbers that were left by themselves that weren't in a pair. Okay, everything had a buddy. You get it? But when you see things like square root of 64, we're not going to do all that. We're not going to do a factor tree. I just want you to write 8, right? So then how about square root of 288? Well, let's think about its factor tree. So we have 2 and 144. Everybody always does 2. So then they'd be like 2 and 72, 2 and 36, 2 and 18. Can we make it better? 144 is 12 and 12. So it breaks into 4 and 3, 4 and 3. So it's 2, 2, 3, 2, 2, 3. And then we still have that 2 from before, so I'm going to drop it all the way down. So we're looking for pairs of items. So we have 2 2's, we have 2 3's. Do we have anything else? Another pair of 2's, right? So everything has a pair except for what number? 2. So that 2 is left on the inside of the square root. Then we get one number from the 2 times 2. We get one number from the 3 times 3. And we get one number from the 2 times 2. Because what are we doing? We're saying the square root of 4, the square root of 9, and the square root of 4. Does that make sense? So our final answer is 12 root 2. Does that make sense? Okay, so some of you might be seeing a little shortcut, which we're going to talk about in a second. But let's continue doing the factor tree. So 32 would be like 8 and 4. 8 is 4 and 2. So it works out to be 2 times 2 times 2 times 2 times 2. There's 5 2's. So how many pairs do we have? We have a pair of 2's there and a pair of 2's there. So how many 2's on the outside and how many are on the inside? 2 2's on the outside, 1 2 on the inside. So our answer is 4 root 2. Does this make sense how we did this? All right, Cam, how are we going to start 180? What do we want for our factor tree?
2 and 90?
You could do 2 and 90. Can we make it better than 2 and 90? You never want to do a lopsided tree, right? If I do 2 and 90, then it's going to be like, oh, it's going to keep breaking down, and then we're just going to have to drop this too. So let's try to not to keep it lopsided if possible. So what's a good way to kind of meet in the middle there? Yeah, you guys are good. 4 and 45. What else? I'm going with the obvious one, Joseph. 18 and 10. I love that you just busted out 4 and 45, though. All right, so 18 and 10. So we have maybe 3 and 6, 5 and 2. So we're going to have 3, 3, 2, 5, 2. So we got a pair of 3's. We got a pair of 2's. One that's all by its lonesome, a 5. So we're going to have 1, 3, and 1, 2 on the outside because we have the square root of 9 and the square root of 4. All right. So we end up getting 6 root 5. That's it. Ooh, 1024. This one is hard to do without 2's. So let's start with a 2. So we have 2 and 512. 2 and 256. 2 and 128. Ooh, 2 and 64. Ooh, we finally got to 64. Can we go from there? 8 and 8. Yeah, let's do 8 and 8. So then we have 1, 2, 3, 4, 5, 6 2's. But then we have 7, 8, 9, 10 2's. So it's 5 2's on the outside. 1, 2, 3, 4, 5, which is what number? Not 10. 2 times 2 times 2 times 2 times 2. Cassie, what do you think? You got it. Yep, 32. Perfect. All right. So this is the factor tree method. It works. It's really great for people in Algebra 1 or geometry. Once you get to things like Algebra 2, Pre-Calc, Calc, we start to do things a little bit faster. So there is a shortcut for doing this. And it's to think about factors that go into it that are already perfect squares. Okay, so going back up to number 2, the square root of 288. The first step we did was 2 and 144. Do you know 144 is a perfect square? Yeah, we knew it went into 12 and 12, right? So what we do is we think about the square root of 288 as being the square root of 2 times the square root of 144. Right, we just break it up into its pieces there. And then we're like, oh, the square root of 2 stays how it is, but square root of 144 is 12, so it's 12 root 2. So see how that can help us? So like 32, what's a perfect square that goes into it? Well, let's look at our list. Our perfect squares. 1, 4, 9, 16, 25. Do any of those go into 32?
4.
4 goes into it. Can I go bigger? 16. If you can get the biggest one possible, it's the easiest way to do it. So we'd have square root of 2, square root of 16. So square root of 16 is 4, and then we have our root 2. So many of you guys are probably good enough to be able to do it that way without doing the factor tree. So when we have square root of 500, what's a perfect square? We know 25 goes into it. Can we go bigger?
Yes, well, no. I have to think.
Can we go bigger than 25? So what perfect squares do we have? 1, 4, 9, 16, 25, 36, 49. Can we list off the other ones? 49 was 7 squared, 8 squared is 64, 9 squared is 81, 100. Does 100 go into it?
Yeah.
It does. Ding, ding, ding. All right, so we're going to think of it as the square root of 100 times the square root of 5, which becomes 10 root 5. So that's our answer, 10 root 5. Faster, isn't it? Now let's say you mess up and you think something goes into it. Like let's say you were on that square root of 32 and you were like, oh, 4 goes into it. And you do square root of 4 and square root of 8. And you're like, oh, 2 root 8. Well, couldn't you go further with the root 8? So then you think about perfect squares that go into it. So we still have the 2 from before, but the square root of 8 becomes square root of 4 and square root of 2. So it's 2 times 2, root 2, which is 4 root 2. So you can get there if you don't think about the biggest perfect square. You can still get there. It just takes a little bit longer. It's kind of like doing that factor tree method. Okay? All right. I don't know if I have more down here. Yeah, we're good. Okay, so it says now try to think about the largest perfect square that goes into each number before simplifying. So for example, if we had the square root of 200, we know that's square root of 100 times square root of 2, so it ends up being 10 root 2. So the perfect square is up to 225. Can we list them out? So 1, 4, 9, 16, that's 4 squared. 5 squared, 6 squared, write them down. 7 squared. 8 squared, 9 squared, 10 squared. What's 11 squared? 121. 12 squared, 144. 13 squared, oh, Cassie, you're good, 169. 14 squared, did you use your calculator? You just know them, all right. 15 squared, 225. Perfect. I have a good friend that works at Sycamore. He always makes his students memorize it up to 25 squared. You have to know all the way up to 25 squared. Can you imagine? All right, so what's the biggest perfect square that goes into 8? 4. So we think of it as the square root of 4 and the square root of 2. And the square root of 4 is just plain 2. So it's 2 root 2. How about 50? 25. So it's the square root of 25 and the square root of 2. And the square root of 25 is 5. So it's 5 root 2. 150. 100 doesn't go into it, right? 25 goes into it. So it's the square root of 25. So whenever I think about 25s going into something, I think about quarters. If I have 150 cents, so $1.50, how many quarters do you have? $1.50 is how many quarters? 6. So it's 25 times 6 is what gives us 150. So how many times does it go into like 225? If I have $2.25, it's 25 times 9. See how quarters can help you? All right, so I have 25 times 6. So square root of 25 is 5, and square root of 6 stays how it is. 288. Yeah, we did. We said it was 144 and 2, so it should be 12 root 2. Does that make sense? Do you guys get that? Yeah, Ian.
Can you break the 12 down, though?
Like the 12 could be like 3 times 4 times, like 3 times 2 times 2. Yeah, but we would want to simplify it and combine those for the final answer. All right, so it says you can multiply and divide with square roots as well. However, we don't leave square roots in the denominator. So square roots can be equivalent, but they can be written in different ways. So this is where I want you to get your calculator out. So it says find the square roots that are the same by finding a decimal approximation with a calculator. So I want you to do the square root of 8 on your calculator. Okay, so when I did, I got 2.828 something. So let's round to 3 decimals. So let's write 2.828. Okay, I used my little approximately symbol. You don't have to use that, but it is an approximation, right? It's not equal to that. All right, so I want you to do the same thing for each of these numbers. So put each of these into your calculator and see what you get. And I'll pause while you do it. Okay, so I think you guys are noticing that these are all the same. Now the hardest one for you guys as I was walking around is this one, the 2 root 6 over root 3. If you put this all into your calculator at once, I would do 2 root 6, and then make sure you end that parenthesis before you start dividing by something else. So then you can do divided by second square root 3 like that, and you get the same thing, right? Same number. So all of these end up being that 2.828. So wouldn't that be a disaster for teachers to grade your test if you wrote it different ways? Can you imagine if Keenan wrote it as square root of 8, and then Jada wrote it as square root of 32 over 2, and then Keegan wrote 2 root 6 over root 3, and then Ian wrote 2 root 2? Ugh. That would be so mean to your teacher, wouldn't it? I'd have to check all those answers to make sure that they're all the same. So what's the most standard way of writing it? What do you think? Square root of 8, but doesn't that simplify? Didn't we just talk about simplifying square roots? Because square root of 4 goes into it. 2 root 2 would be this easiest way of writing, like the most simplified way of writing that. Okay, so we're trying to write it as 2 root 2. Yes? If the square root's already there, it's automatically positive. It's like an invisible sign is in front of it. So she's saying something, she's asking if it should be plus or minus. If we're solving equations and I have x squared equals 25, right? Think about numbers you can plug into x to make that 25. You could plug in both 5 and negative 5, because negative 5 squared gives you 25. So you can't have a negative under the radical. But so if we take the square root, I'll often say, oh, when you take the square root, write plus or minus. So if you're the one taking the square root, you write plus or minus. But if you have a problem that has like square root of 4 plus square root of 9 equals x, that would just be 2 plus 3 equals x, which would then be 5. Does it make sense? You automatically take positive in that case if the square root's already there. We talk about that a lot in Algebra 2. All right, so it says we like to have a standard way of writing these square roots, so why not? So before we had calculators, mathematicians had to do a lot of things quickly in their heads. So there was a chart, like a square root chart, that listed some basic square roots. So it gave things like square root of 2 is approximately 1.414. That's a number that I know off the top of my head. Did anybody know what square root of 2 was in this class? Did you know it was around 1.414? No. It's a little bit more than 1, a little bit smaller than 2, right? So if I asked you to find 2 root 2, would you guys be able to find 2 times 1.414? Could you guys all do that in your head? Double 1.414. 2.828, right? That's what that number is, 2.828, right? That's what we found before. You all can do that in your head. You can all add 1.414 to itself, 1.414 in your head. You're just doubling each digit, right? But if I asked you to find 4 divided by root 2, look at the long division that would entail. 4 divided by 1.414, that was our root 2. Do you guys remember doing long division when you were in elementary school? You'd line them up. You'd move the decimal place over, right? So you'd say, oh, I have 1414 going into 4,000. You'd say, how many times does it go in? It'd go 2 times, so you'd have 2828, and then you would subtract. Do you guys remember doing this? Yuck. We don't want to do this. So we really don't want to do this because it's really annoying, right? Long division is super annoying. So what we do is we do something called rationalizing the denominators. Has anybody ever heard of rationalizing the denominators? So basically, mathematicians don't like to have square roots in the denominator. We like to get rid of them somehow. So you know how with fractions, like if I had 1/2 plus 3/5, what do I do with fractions? Cam, you with me? So if I was trying to get those to have common denominators, wouldn't I multiply this by 5 over 5 and 2 over 2? Right? Why am I able to do that? Why can I multiply by 5 over 5? Does it make my number different? What is 5 over 5? 1. It's 1, right? Can I multiply by 1 and not change my number? Yeah, it's just making it, it's putting it in a different form. So when I have this, what I'm going to do, Max, is I'm going to multiply by root 2 over root 2. And why is that allowed? Because this is 1. It's not changing my number. But what does that do to the bottom? It becomes the square root of 4. Does it just go away? No, it doesn't just go away. It becomes square root of 4, which is 2. So then we have 4 times root 2 over 2. So if I have 4 root 2 over 2, what do you think you get when you divide by 2? What if I had 4x divided by 2? What do I get when I do 4x divided by 2? 2x. So this ends up being 2 root 2. The roots are kind of like x's. We don't do anything there. Just divide the number out front. And that's what we just had here. 2 root 2 was approximately 2 times 1.414, which we could do in our heads, right? So that's the whole point. So we try to rationalize our denominators so that we get something that we can do easily with multiplication, right? Instead of dividing. Long division is the worst. We don't want to do long division. It would be terrible. All right, so this one. So if I have 20 times root 5, okay, you could simplify the root 20, and I could make it 2 root 5, and then multiply by the root 5, or I could combine and say it's the square root of 100. What's the square root of 100? 10. 10. So how about this next one? Root 2 times root 18, square root of 36, right? Over 3. Square root of 36 is 6. 6 over 3 is 2. Done. Okay, so now we're getting into the part where we have a square root in the denominator. So we don't like square roots in the denominator. Because if I was doing 8 divided by 1.414, I would be very sad, right? Don't want to have to do that by hand. That would be terrible. So what we do is we multiply by, if I have square root of 2 on the bottom, I'm going to multiply by square root of 2 over square root of 2. This is just 1. That's why we're allowed to multiply it by it. So the bottom becomes the square root of 4, which is 2. So I get 8 root 2 divided by 2, which is 4 root 2. Perfect. Is it making sense? So the next one, what do I multiply now? Square root of 3 over square root of 3. So I get 15 square root of 3 all over 3, which is 5 root 3. Done. This one has a negative out front, but that's okay. So negative can just stay out front. What's the square root of 25? 5 over 5. So your answer is negative 1. This one's a little gross. You could multiply by square root of 6 over square root of 6. Do we want to do that? Did you guys know that 6 actually goes into 162? Okay, here's the way you can check to see if something's divisible by 6. Cam, wake up, write some notes. So if something's divisible by 6, it's going to be both divisible by 2 and 3. How do I know 162 is divisible by 2? It's even, right? Okay, so I know it's divisible by 2. Do you guys remember the trick to see if something's divisible by 3? We learned this the other day. Add the 1, the 6, and the 2. 1 plus 6 plus 2 is 9. Is 9 divisible by 3? Yes, so it is. So 162 is divisible by 6. So let's go ahead and find 162 divided by 6. See if we can do it without a calculator. So it goes in 2 times. We get 12 here. And then we subtract and get 42. So it goes in 27 times. So we have a negative out front. And when we do 162 over 6, we end up getting 27. Now we just have to simplify the square root of 27. So what's a perfect square that goes into it? 9 goes into it, right? 9 and 3. So the square root of 9 is 3, and then square root of 3 stays how it is. So it's negative 3 root 3 would be how that simplifies. So you could have gotten that a lot of different ways. You could have multiplied by root 6 over root 6, and so on. Okay, so the last little bit that we have talks about going too far. Sometimes you go too far and it makes your life harder. We want to be smarter than the problem. So sometimes you don't need to use the entire denominator as your multiplier. Don't make things harder than they are. So if I just see the square root of 8 on the bottom, yes, I could do square root of 8. But can't I go smaller? I just want to get it so that when I take the square root of it, it goes out evenly. It comes out even. Not even, but comes out clean with no square root. What's the smallest number I can multiply square root of 8 by to make it a perfect square?
2.
Square root of 2, right? Do you guys see it? So all I need is square root of 2 over square root of 2. So the top becomes 2 root 2. The bottom is the square root of 16. And the square root of 16 is just 4, right? So we get 4 down there. Can we reduce this at all? Think about if you had 2x over 4. Can't you reduce the 2 and the 4? Yeah, so let's do that. So let's make it root 2 divided by 2. So we're just reducing this like that. Okay, so it's 27. Ooh, this is a hard one. Think about our perfect squares. If you get this, I'll be really impressed. The smallest number we need. Think about how 27 is. Isn't it 3 times 3 was 9 times another 3? How many more 3's do we need so that we have an even number of, so we have pairs for everything, I guess. Yeah, I need one more 3, right? And 27 times 3, it ends up being 81, right? So I have the square root of 81 on the bottom, which comes out evenly. It becomes 9. Can we reduce it at all? Yeah, 3 and 9 becomes 1 and 3. So we end up getting square root of 3 over 3. And that's our answer. Okay, the next one. Do you see any shortcuts? You could, like you could divide it out. So let's do, so we do negative, and we're going to put 1,000 over 500. So Colin's saying divide by 10 again. So we divided by 100 on both of them. That's okay. They're both under a square root. Simplify. What's 10 over 5? Yeah, so isn't it just the square root of negative square root of 2, I guess I should say. Yeah, that's it. So that one we didn't have to multiply by anything on the denominator because we could have just recognized that 1,000 divided by 500 reduced out to 2. And that's our answer. Okay, does this make sense? Do you guys get square roots? All right, let's stop there.